Without further ado, it's my pleasure to introduce Keith Winstein, who is a PhD candidate at the Massachusetts Institute of Technology. So back when I was starting to be a graduate student, 1999, 2000, there was this general malaise in SIGCOMM and networking researchers that TCP was so tired and so boring and so done, and it was the example of incremental work which nobody should do anymore, and there's just this tremendous, gosh, we've been doing this for so long, what came of it? But now it's over a decade later, and the internet has changed. It's changed in a whole bunch of very interesting ways. And it means that actually, in my opinion, some of the most interesting research going on right now is about what TCP might look like in the future going forward. And this is probably of tremendous interest to you, given what you've been studying. And I think that some of Keith's work is some really groundbreaking, interesting work in this space. And so please welcome Keith to kind of tell you maybe where TCP will be in 5 years.
Thank you very much, Professor Levis and Vimal and Professor McEwen for having me here. I'm Keith Winstein, apparently from the Malaise Institute of Technology, but I'm here to change that. I'm here to talk about congestion control. This is the most important topic in computer science, I think you've all learned. It serves multiple masters. What is sort of the, can we agree, what is the purpose of congestion control? Have you guys studied congestion control? Okay, what is, last week? Okay, you sir in the box shirt, what is the purpose of congestion control? They're like, oh, the invited speaker's not allowed to do that. What is the point of congestion control?
So what happens is, you don't want to hold a network, right? You don't want many packets to go and make more delay to the network, so that's why you have.
Yeah, I agree with that. I think that's exactly. You don't want to overwhelm the network. That's congestion control. You don't want to cause congestion collapse. I think we have this fable. The internet started, there was no congestion control. 1988, the whole internet collapsed. Heroes rode to the rescue, heroes from Berkeley, and they fixed it. They added congestion control, and since then, the internet has been the biggest engine of world commerce we've ever seen. That's sort of the traditional fable. You guys agree with that? There's a sort of more recent view, which is that congestion control is not just about preventing calamity. It also has a role to play in the common case. Congestion control is what allocates the limited resources of the network to different users. So when I'm in my house, I have a 10 million bit per second connection to the internet. If I'm trying to upload a video to YouTube and my friend is trying to upload a video to YouTube, do I get 9 megabits and she gets 1? Or I get 5 and she gets 5? Who decides the allocation of the limited resources of the network? Does the network decide? What do you think?
Me?
Yeah.
I think the network decides in some cases, depending on how it controls flow.
How would it decide?
Sometimes it has a queuing system, so like fair queuing or weighted fair queuing.
That's true. Do you have that in your house? Do you have fair queuing? Yeah. I think typically in my house, a packet is a packet. And so anyone who sends a packet, it just gets in line with all the other packets. So the network sort of doesn't decide how to divide up resources. And we're sort of proud of this. We say, we have a dumb internet and a smart endpoint. Have you guys heard this? All of these decisions. Is that Adam? Oh my God, everyone I know is in this room. OK, sorry. We have a smart endpoint and a dumb internet. And we're sort of proud of this, because having a dumb internet means that you can start Skype. You don't need the permission of the network. You can start Facebook. You don't need the permission of the internet. We're sort of proud of this end-to-end principle. And so congestion control, we can do it purely end-to-end, or not necessarily. And as Phil says, there's a long lineage of these congestion control schemes. So starting in the 80s, we had these celebrated schemes here, TCP Tahoe especially, also DECBIT, all these early schemes which were purely end-to-end for sharing the network, for congestion control. We've also had schemes that involve functionality in the network. Weighted fair queuing, for example, as the gentleman there mentioned. That was the 80s. And then in the 90s, there were more of these schemes. There's TCP New Reno, I guess you guys have studied a little bit. And explicit congestion notification in red and blue, more schemes. This is maybe sort of where the malaise kicked in. And then here was the 2000s. There was like an explosion. Like once something gets over, that's when everyone else starts researching it. So there's hundreds of schemes here. Now there's the binomial TCP, I think is my advisor's work, right? Yes, OK. So binomial TCP, he's never going to watch this. Fast TCP, compound TCP. And then we've had these schemes inside the network, XCP, RCP, VCP, all these new schemes. And then in the 2010s, we had even more of them. And in fact, even in the most recent SIGCOMM, where we first presented this work, there were still more schemes. I think there's pFabric and FCP, all these ones, general aggression from Google. So there's like a whole tree of these schemes. And there will be a test on all of these. You're going to have to identify the salient features and what they differ. So look, I am not here to add more fruit to this tree. I don't have another box to show you. That's not what this talk is about. I'm here to ask a different question, which is to say, if all those little boxes are the answer to some question, like what is the question? Like TCP new Reno, what is the thing you could ask where the answer would be, oh, TCP new Reno? Do we know the answer to that? Like, what is the problem for which new Reno is the solution? Yes, sir.
Bursty losses.
Bursty losses. Yeah, like congestion losses. And maybe congestion losses, and what does new Reno want to do about them?
Don't know.
Yeah, it's actually a really hard question. No one knows this. This problem is called the teleology of TCP. What are the ends that TCP is trying to achieve? TCP is the means, and what are the ends? We don't know the ends. But maybe we can start to try and answer this question. And if we can be really precise and say, okay, this is the problem, this is what congestion control is trying to solve, then we can ask, okay, once we've been precise about the problem, now are there any better answers to that question? Maybe TCP new Reno, TCP cubic is not the best answer. Maybe we can come up with a better answer once we get really rigorous about the problem. So that's what I'm here to talk about. Because right now, it's really hard to sort of formally even debate which system is better. I don't know if you guys have studied, but right now in Linux, cubic is the default TCP scheme, the default congestion control. And in Microsoft Windows, compound, in some versions of Windows Server, compound is the default scheme. Which one of these is better? Say we asked that question today on Hacker News. Which one is better, cubic or compound? Would there be like an erudite debate in the comments? What do you guys think? Like, how would you even answer this question? Like, you guys have studied these schemes, right? You studied Reno and new Reno. OK, is new Reno better than Reno? What do you think, sir?
Yeah.
Yeah, why is it better?
It increases your average throughput.
My average throughput?
Everyone's average throughput. If you average
Everyone's average throughput goes up.
If you average all of them together.
I don't know about that. Do you think there's anyone that new Reno hurts?
Probably someone.
Yeah, probably. So there's some sort of assumptions that go into this. Like, we think new Reno is better, yeah, but there's some assumption that new Reno makes that we think it's probably better for most people if you assume that most people are like something. But these assumptions are sort of explicit. Seriously, the assumptions are implicit. We can't really say, cubic versus compound, do they have different goals? Are they trying to achieve different things? Maybe they make different assumptions about the network. Or maybe one is just plain better than the other. We can't really answer these questions. It's very hard to say, like, who are the people where Reno is better and who are the people where new Reno is better? We don't really know how to answer these questions. And as a result, like, everyone who builds things at the lower layers, like the network, is sort of constrained by this fuzzy idea of, like, what is it that TCP wants? So let's say you guys are going to invent the next Wi-Fi or the next LTE. You're going to have to design it in a certain way to make TCP happy. But we don't really know what it takes to make TCP happy. There's this document here, RFC 3819 from like 15 years ago. That document's up to 60 pages. And if we updated it for the last 15 years of TCP, it would probably be like 9 million pages. Like, there's like all these rules. It's like a religion of like what you have to do just because TCP says so. Or like, we don't really know. Like, TCP's off in the cloud. We just have to do all these things because we think TCP wants this. So for example, we think TCP doesn't like it if you drop packets. Like, let's say your Wi-Fi. You send a packet, there's a little bit of noise, so the packet gets lost. What should you do? If you're Wi-Fi, should you try and resend the packet? Or should you let TCP deal with it? What would be the benefits of letting TCP deal with it?
Simplicity.
Simplicity, yeah?
If you have other protocols, then you're not messing up those protocols, right?
Yeah, some protocols might not want reliability. They might just want low latency. So letting the endpoints deal with it is a lot better. If it's a video program, you might not want to resend the old frame. You just send the new frame. So that's the benefit of letting the endpoints deal with it. What's the benefit of having Wi-Fi deal with it? What about if Wi-Fi just was totally reliable and every packet you send to Wi-Fi gets to the next hop? Why would that be better? How you, sir? Yeah.
It reduces complexity in the TCP layer.
Yeah, reduces complexity in the TCP layer. How so?
If it doesn't have to worry about reliable transmission, because Wi-Fi guarantees that.
That's true. That's true if TCP can rely on that. You're right. If we just made everything in the internet reliable, then the endpoints wouldn't have to worry about reliability. Did they debate that in the 70s and 80s when they were making the internet?
I would assume so.
Yeah. So you're right. There's been a lot of debates about this. Should the reliability be in the network or should it be end to end? It would be arguably simpler if every link worried about reliability. That's not the way we've shaken out. So as a result, so the problem is TCP does want packets to get delivered. TCP assumes that when a packet is lost, what does that mean? What does TCP do when a packet's lost?
Reduces the congestion.
It reduces the congestion window. It says, oh, a packet was lost. There must have been a queue inside the network somewhere that overflowed. So obviously, me and all the other TCPs were sending too much. We all got to back off. Right? You've talked about additive increase, multiplicative decrease. So TCP assumes that when packets are lost, that's because of congestion. So that's not true if Wi-Fi is dropping packets because of loss. So the TCP sort of has this implicit assumption that when a packet is lost, it better slow down. So for that reason, Wi-Fi can't lose packets. It has to try and retransmit them. It has to try and sort of pretend to be reliable, because otherwise TCP is going to freak out. So we end up with things like this buffer bloat problem, which you guys have studied, right? So why do you think there's buffer bloat? You, sir, in the blue.
Because one flow overwhelms the buffer queue.
But why do we have these huge buffers in the network? Why did
Because then less packets get lost.
less packets get lost? Yeah, because people who design these networks think, well, we're Comcast. We're trying to sell someone 20 megabit per second internet service. We want them to download a file from the internet, get 20 megabits per second. So by golly, we don't want TCP to slow down, because that's how the customer is going to judge our service. So we better never drop a packet. And Verizon does this. Anirudh and I have met with Verizon. And we show them, look, Verizon, you're holding on to packets for 60 seconds. If we flood you with packets, you have such a huge buffer, you'll give us a packet a minute later. And we say to these phone company guys, why would you do that? No one cares about the packet a minute later. Like, why don't you just drop the packet? And they say, you guys don't get it. Like, we have 5 nines of reliability. We're the phone company. We have 99.999% reliability. You're asking us to have less reliability. Why would we ever do that? You will just make TCP go slower. Why would we do that? So sort of the assumptions of TCP are affecting the behavior of the network. And the network stores all these packets forever because they think, oh, TCP doesn't like packets to get dropped. On the internet, we rarely route flows over multiple paths. You can imagine from Stanford to MIT, there's many ways to go. You could send it through Canada, you could send it through Mexico, you could send it directly. It might be beneficial to use all those paths, right? You might get 3 times the throughput. But why don't we do that? Yes, sir.
Because you're sending multiple paths and you're not, in-order delivery isn't guaranteed, right? So you might keep sending.
Right, exactly. You might get out-of-order packets. Now, what's the problem with out-of-order packets?
It's not TCP.
TCP will freak out. Yes, sir.
Well, that answered it.
Oh, yeah, TCP will freak out, yeah. But like, if you're downloading, like, what is the main user of TCP? Like, what is most internet traffic? What application?
Video.
Yeah, it's the web. Yeah, exactly. And like, does the web care if you get like part of an HTML file like in a different order? Like, no, you just care when you get the whole file, right? So like, TCP will freak out because TCP interprets out-of-order delivery as a pathology, and so as a result, like the whole network cannot use multipath. But, like, this seems terrible. Like the network should be free. Like if the network can give me multiple paths and make it faster, like it should. So the applications too are sort of hacking around TCP. TCP has sort of like one idea of what the application wants. Like if you're FTPing something, we assume like, oh, you want that file transfer to complete as soon as possible. But a lot of applications are not like this. So some applications open lots of flows. They pretend to be like 10 TCP connections. What happens if I'm trying to have a conversation, I have 1 TCP connection. Meanwhile, someone else opens up 10 TCP connections. What's going to be the split in the throughput? Do I get half and the other application gets half? No, I get like a tenth and they get like 90%. Because they're like 10 times more flows. So are there any applications that do this? Well, what would be an application that opens lots of TCP flows at the same time? What was that?
Yeah, web browser.
Yeah, like all of them. Yes. So these applications are all like sort of cheating. They're all opening many flows to get many times the throughput. But all these poor guys who have only 1 flow, they get screwed up. Or people cheat on the sort of slow start phase. Like who would do such? Like what evil entity would do such a thing like that? Like who would cheat the slow start? Or they try and stop these buffer overflows, these queue overflows. So they add pacing to TCP like by themselves to try and stop that from happening. This like obscure web service. Or increasingly the application just says, you know what, like TCP is not for us. Like TCP is a one-size-fits-all thing, and we are a special snowflake application, so we're going to make our own congestion control. So this is happening more and more. The Chrome web browser now includes experimental support for sending web traffic over UDP and doing its own congestion control. BitTorrents over UDP. The Mosh roaming SSH programs over UDP. And this file transfer application, Espera, Hollywood uses this to send footage. When they go to Europe, they film a movie. They want to send the daily footage back to Los Angeles. TCP is really slow on those links, those long, fat pipes that have a real long round trip time between Europe and Hollywood. So they use this Espera program, which just sort of cheats, just sends packets really, really fast. So this is sort of the status quo. So I think it would be better to sort of free the network to evolve and do the things that are like good ideas, like multipath routing is a great idea, and dropping packets might be a great idea. Better than like spending a minute trying to resend the same packet. So like it would be a better idea if the network could do whatever it was going to do, and the application could say what it wants, and then the transport layer like TCP can adapt to that. I think that would be like a better way to do things. So what we've built is this program Remy that's like a first step in that direction. Remy is an optimization tool. You can download it from GitHub. It's a program that generates congestion control schemes. And we're very formal about what the input is. It generates congestion control schemes as a function of the assumptions you make about the network. So what might the network do? It might be a network that can drop packets or a network that doesn't drop packets. It might be a network with long round trip times or one with short round trip times. We have some sort of fuzzy model, an uncertain model of what the network might do. And we have a model of what we're trying to do. What does the application want? Does it want just bulk throughput? Does it want low latency? Does it want some compromise between those things? So you encode these two things, the assumptions of the goal, you put them into Remy, and you pay $10 to Amazon, and at the end, like hours later, you have a congestion control scheme. So that's the actual thing that we built. So how do we do this? Should I stop here? No, I'll go on. OK, how do we do this? The goal of this Remy program is to generate a congestion control scheme. We call this a Remy CC, a Remy generated. It's a computer-generated congestion control scheme. Any scheme has to answer like this question. This is like the question. There's like pretty much this is it. So like you guys have learned about TCP Tahoe, the basic TCP. Like how does that answer this question? Does it at any moment in time can Tahoe tell you whether you send a packet or don't send a packet? Yeah. That's pretty much what it does. In any scheme, Vegas or Skype or anything has to pretty much answer this. So we really only have to answer this binary question. Do we send a packet or not send a packet? Yes, Professor Maziris.
You mentioned multipath multiple times. The question might be a little more complicated, like how do I send the packet?
That's true. That's true. So the simplest model we have here is one where the endpoints don't control the routing at all. The network does what it wants, but the sort of only endpoint actuation is introduce a packet on the path. So you're right. There could be more control. You could set certain bits in the header, like some source routing or a diffserv code point. You might
or even multiple IP addresses.
That's absolutely right. Yeah. So we haven't studied that problem. So that's the question. And in service of what goal are you trying to solve this question? So you could try and optimize some objective. So we want to be very precise about this goal. A lot of people try and optimize this one, the log of the sum of the log of the throughputs. So if I'm in my house and we have this 10 million bit per second connection to the internet, and it's me and my friend, and we're trying to upload, what will be the solution, the division of resources that optimizes that? The sum of the log of my throughput and her throughput. Evenly, yeah, exactly. Yeah, because a log is one of these functions with diminishing returns. So if you give it 5 and 5, that's the best you can do. What we're going to study is close to that. We're going to have this proportionally fair throughput divided by delay. So we're going to reward throughput and penalize delay. And you might ask, what if delay is more or less important? So we can put a little annotation factor here. We can say delay is really important to me, or throughput's really important to me. There's many other objectives you could have for congestion control. You could say I want to minimize the average flow completion time, or some complicated transaction like page load time, or some tail of the completion time. You can have any objective. And I am totally agnostic as to what your objective might be. But anyone who comes here to you with one of those boxes on the little chart at the beginning, you should ask them, well, what is the objective of your little box, of your big box? What's the objective of your box? This should be a question that any system designer should be able to answer. Like, what am I trying to achieve? So that's the objective. We also want to encode these prior assumptions. Like, what is it that the protocol is entitled to know before we begin? Do we know the speed of the network? Some of these schemes do know the speed of the network, like the XCP scheme, for example. The gateways know exactly the speed of the network. Sometimes you don't know at all. You could be on a modem. You could be on a satellite link. You really have no idea. So can we have some uncertain model about the distribution of networks that our flow is entitled to assume before it begins? So the classic network that we study, this dumbbell network, we have a sender. It introduces packets to the back of a queue, and they get drained at some rate by a link, like a fixed rate link, like an Ethernet. They go to the receiver, and acknowledgments come back with some end-to-end delay. So this problem, let's say the link speed were known. This problem is pretty simple. The best thing you can do is just send packets at that link speed. But of course, this is not the whole problem, because what makes it hard is there may or may not be some other flow contending for the same bottleneck. And there could be an arbitrary number of these flows. So the problem here is to figure out when to send a packet or not send a packet under uncertainty about the link speed and the round trip time and whether or not there are other senders and how many of them there are. All right, is that clear? All right. So, and I'm going to further simplify the problem to say we're going to solve this problem super rationally, which is to say I am the protocol designer. I'm going to design one algorithm, and all of the nodes are going to run that algorithm. So the question is just, what should that algorithm be? So we could say, if I'm an evil person, and I know everyone else is running TCP New Reno, and I just want to get the most throughput, what would be the rational thing for me to do? What's the best? If my goal is to get the most throughput, I know everyone else is running TCP New Reno. What should I do? What's the rational thing? Yes, sir.
Open up a bunch of connections. Send us
Yeah, just like send a ton of packets. Just keep more and more packets, or open more and more connections, as you said. What's an application that opens tons of connections to the goal to try and get most throughput? BitTorrent, exactly. Yeah. So that's the rational thing to do. Is everyone should just run BitTorrent. We should just flood the network with many packets. So the most rational thing ends up being a congestion collapse. So this is not that. This is the super rational thing where I say, you know what, I'm quite rational, but so is everyone else. And anything I'm going to do, they're also going to do. So really the question is from the perspective of the protocol designer. We're going to design one TCP, and everyone's going to run it. And what should that TCP be to maximize everyone's happiness? Yes, sir?
If you're designing this program to give unique protocols to everyone?
No, we'd give one protocol to everyone. The same protocol to everyone.
Okay. So,
yes, sir?
So the scope of this is like for the entire internet as opposed to for like a particular wireless network or cell phone network or something.
Well, so Remy designs a congestion control protocol for a TCP/IP type network. I don't think we're ready to say that we could design one that would be appropriate for the whole internet. I think at the start, maybe we'd just design one for a data center or a particular link where there's a known population of nodes contending. And we could test it by installing the Remy CC on those nodes and seeing how well it worked.
But basically, you assume all the people who are competing are transiting roughly the same networks. It's not like one person's going over a wireless network and then the rest of the internet, and someone else is just going over the rest of the internet, and you're worried about how they compete.
Yeah, certainly in this talk, I'm not going to get into those kinds of problems. Yeah, absolutely. So we're trying to distill this problem sort of to its essence, which is to say there's an almost a known topology, and the only uncertainty is the link speed and the number of nodes and the round trip time. So we have sort of limited uncertainty. Yeah, that's a good question. All right, so we wrote this program Remy, and it searches for the best congestion control protocol. And by best, we mean the one that when everyone runs it, it optimizes the expected value of that objective function. So in general, this is a really hard problem because there's a huge number of these functions that relate the whole history of what you've done and all the acknowledgments you've received. That's the input. And the output is, do I send a packet now or not send a packet now? That's way too hard. That's like 2 to the 2 to the n. So we're not going to do that. We're going to dramatically simplify the problem by limiting the available state that we keep track of. So a Remy CC is only going to keep track of 3 signals. It's going to remember a moving average of the time in between the acknowledgments it's getting from the receiver, a moving average of the sender timestamps that it sent and then got echoed in those acknowledgments, and the ratio of the most recent sample of the round trip time to the smallest one it's seen so far. So those are the 3 signals. Yes, sir?
Yeah, so it's interesting is you're not looking at actual losses and you're just looking at timing. Is this like influence from spout, or you're looking at just the timing intervals as opposed to the actual sort of inferred losses or expected losses?
Yeah, so there's a sort of respectful and a more idiot savant answer to this question. The respectful answer is that when you create a protocol that tries to reward throughput and minimize delay, you end up seeing very few tail drop losses because you don't exceed the buffer size because the protocol is trying to keep the delay small. So loss ends up not being a very useful signal in this case. So TCP sort of depends on loss. The model of TCP is we're going to fill up the buffer until it starts dropping packets, and then we're going to modulate the congestion window so that the loss is acceptable. But if the goal of the protocol is not to build up a delay, then you never end up filling the buffer. So we get almost no congestive loss. That's the respectful answer. The idiot savant answer is that I don't have to know the answer to these things because I'm not the one creating the protocol. The computer's creating the protocol. And we can look empirically at the value of these congestion signals. So the idiot savant message is actually the real message of this talk, which is to say, in systems design, we make all these choices sort of heuristically, like what do I, Keith, think is important? But I'm not like that smart. Like the computer is smart. So like anything I could do, I should be able to teach to the computer and have it reach the same conclusions. Like this is how we check our work. So we can check empirically what is the value of an extra congestion signal. So we can give the Remy optimizer, we could add to this list loss or RTT difference or all kinds of different variables, and we optimize and we see, did it get any better? Or maybe not. So sorry, yes?
Yeah, so feature selection.
Yeah, we are doing feature selection.
Did you do that and then find that these features were the dominant features?
I did.
Okay.
Yeah. I mean, this was like, I told Hari, like, I will have a paper for SIGCOMM, and then I'm like up at 4 in the morning. I was like, oh, that one didn't work. Oh, that one didn't work. Oh, that one worked. Yeah, then you want to come into your advisor the next day and be like, I found something that worked. I mean, that's a very motivated problem. But the computer guides the selection of the algorithm. So I think almost any time in system design it can be helpful to think about like, well, can we sort of more rigorously explore the space of choices here? And so these are sort of dumb choices. They're dumb in that I didn't really make them. It's just these are the ones the computer found was helpful for these kinds of networks. And if you ask me, are there other networks where different signals were helpful? That's a question I would have to study empirically. It's not one I can sort of reason about off the top of my head. So that's the answer to that one. And then the goal of a Remy CC is to just map these 3 input variables at runtime to 3 output variables. So we come up with this mapping. And the output variables define the runtime behavior of the algorithm. So we have a congestion window, which you guys learned about. And at runtime, we multiply it by something, we add something to it, and we enforce an interval between outgoing packets. So this is sort of the runtime algorithm. This is like all of TCP, which is to say, when you get an acknowledgement, you put the 3 input variables in, you get these 3 output variables, you update the congestion window, and then you send a packet if you can. That's the entire algorithm. All right? So I want to take you through how the optimizer works. So the job of Remy, as we said, is to find a piecewise continuous mapping between those 3 input variables and the 3 output variables. So how does the optimizer work? It's really hard to show this three-dimensional mapping on a slide. Actually, Vimal prepared a whole thing showing that mapping, but he didn't show me. He only showed Anirudh. So I don't have that. So I can't show you 3 dimensions to 3 dimensions on a slide. But what I'm going to do, I'm going to dumb down the problem. We're going to only look at a 2-dimensional mapping. So we're going to make a dumb Remy CC that only gets these 2 signals and maps them to these 3 output signals. So I said we had to be really precise about our prior assumptions. So these are the assumptions that went into the run of the optimization. We have a dumbbell network. The link speed is drawn from this uniform distribution. The round trip time is drawn from distribution. The number of contending nodes is drawn from distribution. And all those contending nodes switch on and off according to some stochastic process. So those are the assumptions. And this is our objective. We're trying to optimize the log of the sum of the log of the throughput divided by delay for every sender. And so we start out with this mapping. So the first input here, that send moving average, is on the x-axis. And the other input, the congestion signal, is on the y-axis. And then the output is going to be some action. It's going to be some multiplier, some increment, and some pacing interval. Is everyone clear on what I'm talking about that action, those 3 output variables? So when we start out, we don't really know what the action is. And to find the best action, we just sort of search for it. This is pretty brute force. We use sort of a gradient descent. And we say, look, if we have an algorithm that only has one possible action, so no matter what comes in, it has to do the same thing, what should that thing be? And here's the answer. If you have only one thing you can do, by golly, you should deduct 10% from the congestion window, add 4 to it, and enforce a 3.3 millisecond interval between packets. Now, it's kind of silly. Like, what is the point of having these signals if you're not going to do anything different in response to the values of the signals? So what we do next is we split this rule on the median query. We find the place where 50% of the query volume is here and 50% of the query volume is here, and we just split it. And then we run the rule and we see which ones actually get used and which don't. And then we optimize each one separately. So now we have 4 separate actions for these 4 different regions of the sort of state space. And then we just split it again and simulate it and optimize it. And so we just sort of run this over and over again. And we end up with this sort of very smooth function that maps between the input variables and the output variables. So that's how the thing runs. It's a really pretty dumb brute force kind of thing. All right? So that's how it works. Now let's talk about the evaluation. So we posted all this stuff online. We compared against TCP Reno and Cubic and Compound in Vegas. and also the in-network schemes, SFQ CODL, this is fair queuing with CODL, which is an in-network scheme, and XCP. So we're comparing against end-to-end schemes and in-network schemes. And we publish the whole setup on our website. So you can go to our site, you can click the reproduce the results button, and you can reproduce everything. So we encourage you to do that. And you can get the same plots I'm going to show you. So we're looking at this dumbbell network. So these were the same assumptions over here, and then we had these parameters here were the actual parameters of the simulated network. So we didn't tell Remy exactly what was going to happen, but we gave it parameters like the link speed is 15 megabits per second, which is in the middle of the range that we told Remy to assume. So when we look at what happens, we're going to show the results on one of these throughput versus delay plots. So the throughput, up is better, up is more throughput. And on the delay, we flipped the x-axis. So the best delays are over to the right. The smallest delays and the best delays are the right. So the best is sort of up and to the right. So if we look at TCP New Reno, which you guys have studied, we had 8 senders. So when we run the simulation, we get 8 dots. And this is what happened. These are what the 8 senders achieved. So this guy got very good throughput but bad delay, and the other 7 didn't get that much throughput. So TCP New Reno is not that fair. This is one run of the simulation. If we run it many times, we get many dots. And we can sort of summarize these. We can look at the median and then the 1 sigma ellipse. So what does this ellipse mean? This is the median, and then the height of the ellipse is sort of how unfair is this scheme in throughput. And the width is sort of how unfair is this in delay. So the ellipse sort of expresses 4 variables. It's what's sort of the median throughput and delay of a TCP New Reno world, and what is the amount of unfairness in throughput and delay. Is this clear to everybody? All right, so that's TCP New Reno. Let's take away all the individual dots. Here's the other end-to-end TCP schemes. So TCP Vegas is the most concerned with delay, and it gets the least delay, but also the worst throughput. TCP Cubic gets the best throughput, but also the worst delay. TCP Compound is sort of, it is a compound of a loss and a delay-based scheme, and it's sort of in between Cubic and Vegas. So that's kind of nice. Now we can look at the in-network schemes. These are schemes that have code actually running on the routers. And these are right here. So you can see these schemes are a lot fairer than the end-to-end schemes because they use intelligence at the routers to adjudicate among flows. And they get more throughput. Although in this case, they also get worse delay. So there's some compromise here. And where are the computer-generated schemes? They're over here. So we get 3 schemes that have 3 different importances for delay. So there's the one for which delay is most important, this delta equals 10. He gets the best delay. And there's one where the throughput is most important, delta is a 10th. He gets the best throughput, but worse delay. And we can sort of plot the efficient frontier here. These are the schemes, no matter where you are, you should rationally prefer to be on that frontier. So the computers are destroying the humans. And in fact, the computer-generated end-to-end schemes are dominating the human-generated in-network schemes. I don't think you would have predicted. I think most people think, if you can have code running on the router, wow, that's incredibly powerful. You might think that is the best you can do. But actually, you can do better end-to-end if you're a computer than if you're a human. Even a professor at MIT writing code runs on the router. I don't think that's a surprising scheme. All right, so that's on that dumbbell network. Oh, yes, sir.
Patterns that you used?
So
everybody always can send, or?
So the traffic is the nodes switch on and off. They switch on to send a certain amount of bytes drawn from an exponential distribution with mean 100 kilobytes. And then they switch off for an amount of time, mean 1/2 of a second. All right, so that's one network. We can also look at a sort of wireless network with a varying length. This is not one that the Remy CC was optimized for, but it still works pretty well. This is a Verizon LTE trace. You can see the Remy that's sort of compromised between throughput and delay. It's probably the best sort of overall, although the Remy here that cares most about delay is beaten by TCP Vegas. So you might ask, how important is it, the prior knowledge that you supply to the Remy? I think this is a question you should be asking. Keith, you told it that the throughput would be between 10 and 20 megabits per second, and you gave it 15, or you gave it that Verizon. How important is that prior information? Maybe it's just cheating because you gave it all the important stuff a priori. So we can look at that. So we looked at a Remy CC that we've designed for this shaded region here. We told it the throughput would be between 4.7 and 47 megabits per second, so a 10-fold range. How well does it do inside that range? We compare that with a Remy CC that was designed for a particular link speed, exactly 15. And you can see that when the real link speed actually is 15, that Remy CC does the best. But when we start to violate those assumptions, it does really bad. So it appears perhaps this prior knowledge is helpful, although it doesn't do that much better at 15 than the one that's optimized for a 10-fold range. So it's not totally clear how important is it to give specific prior information. And if we optimized a Remy CC for a 1,000-fold range or a 10,000-fold range, which is, I think, what you'd have to do if you wanted to run for the whole internet. Because the internet, I can be on my 14.4 modem, or I can be on 10 gigabit Ethernet. You'd have to have a Remy CC that admitted both as possibilities. For technical reasons, we haven't been able to do that yet. So we don't know yet how much we'd compromise in the height of the performance to spread it out 10,000-fold. We do look at an in-network scheme, this cubic over fair queuing and coddle, and you can see it's much more consistent than the computer design schemes. But within the assumptions that we told the program it was entitled to assume, the computer design schemes do way better, even though they're end-to-end. And if you looked at TCP Neurino on this chart, it would be like below the floor, because these TCP schemes fill up the buffer, so it would have a terrible delay, because we're looking at we're penalizing it for delay here. So this question of how important is it, the prior knowledge was sort of motivating for me. So I think it's important to think about, could we move towards formalizing sort of this idea of systems design? Many design choices, and not just in networking, well, certainly not just in congestion control, and not just in networking, represent some sort of implicit optimization or a heuristic trade-off. And I think we should sort of train ourselves to ask, well, what in the landscape of possible choices, what was the choice that we make here in this system? And can we sort of position it among the alternatives? I think this is sort of a good thing to think about. And we've done this. Actually, you have done this. I haven't done it, but you have done it. But we've all done it. Anirudh and I have devised a prior algorithm, a human-designed algorithm for cellular networks. Cellular networks are challenging because they vary in speed. You can have a 50 megabit per second link from Verizon, and then you drive under a tunnel, it goes to like a no megabit per second link, and then good again. So trying to design a scheme for this network is pretty challenging. So we designed one. It was at NSDI last year. And two Stanford students, Alterman and Kwok, reproduced our measurements for the Stanford CS244 class last spring. And it was like, they wrote this blog post on the Reproducing Network Research blog, and it was like a huge effort. And these students actually won the Best Project Award in CS244 last year, which, I think I took it as a compliment. I don't think it meant that Anirudh's and my work was the most difficult to reproduce. We were so bad that these students had to go through heroic efforts to manage to, I don't think that's what the award represents. I hope not. But we did think, yeah, well, we're inspired by that example to have the reproduce button. So, but we did think, if Stanford students are getting awards just for replicating our work, we want to sort of surpass you guys. So we ran a contest at MIT. We gave MIT students prizes for actually beating our work. So we took this earlier algorithm, which was called Sprout, and we told the students, look, we're going to take the evaluation, we're going to package it up in Mininet, which you guys have developed, and we're going to let them run it as a contest. So you make your own congestion control algorithm, and we'll run it, and we'll see how well you do. And you're going to try and optimize throughput divided by delay. And fourth place in the class will get $20, third place $30, seventh place would get $40. And if you actually beat Sprout on this throughput versus delay metric, we would give you the grand prize, which is that you get to be on a paper with Winstein, Sivarman, and you at the next NSDI. So that was the prize we offered the MIT students. And when we did that, it was like a little pause, and they were like, well, how about $50 instead? So, I don't know. So we did this. So we gave the students, this is the baseline. This is how Skype performs on this Verizon LTE trace. This is how our algorithm performs. And this is how the best you could possibly do perform. So, I think we should always try and have these graphs. What is the best we could possibly do? How good are we? And how good is the competition? And then how good are 3,000 attempts by all of MIT students? So the students they tried everything they could think of. There were these machine learning grad students in the class, and they tried boosted random ADA forest, and who the hell knows. And they got all these options. And I think if you look at the sort of convex hull of this, it really suggests there is a landscape of trade-offs. And Sprout, our algorithm, is not the best you can do because there is no best. But we've made a particular trade-off between throughput and delay. And maybe you want to be here, maybe you want to be here. And we should talk in those terms. So I would urge you to think about these sort of new trade-offs. With Remy, traditionally we had simple rules at the endpoints, but they produce very complex behavior when you run a whole network running TCP. With Remy, we get very complex rules at the endpoints because they're designed by a computer that makes crazy things, but you get much more consistent behavior overall. And you can get some surprises, like the fact that end-to-end algorithms can surpass in-network algorithms. I wouldn't have guessed. So the message sort of Remy is that the network is evolving, or at least it wants to evolve, and TCP shouldn't be holding it back. And the message of my talk is we should think about all these little boxes we're learning about, the congestion control schemes, what is the problem for which these guys are the solution? And if we can be precise about that, maybe there's another avenue we can go down. So that's sort of the message I want to leave you with. Thank you.